Welcome to the 2025 PIBBSS Symposium. Our speaker is Jasmina, and she'll be talking about the computational mechanics of transformers.
Yeah.
Take it away.
Thanks a lot, Carlo. I'll be talking today about the project I worked on during my PIBBSS fellowship, and we'll be continuing with the topic of computational mechanics, but this time now taking a lens on the transformer training dynamics. The project has been mentored by Adam Shai and Paul Reichers, and I'd like to start with, let's see if I can move the slide. There it is. A brief motivation on what inspired the project and what the main goal was. And that was to characterize phase transitions during the training process for transformer models. And we want to do this by using two frameworks. The first one was, of course, computational mechanics and using tools and methods from that. And the second one is a framework that's very well known, in information theory, rate distortion. They are combined in a work from some years ago from Sarah Marson and James Crutchfield in a single framework called causal rate distortion, which I'll be explaining in more detail in the upcoming slides, but I would like to take some time here to just give the high-level idea of this framework. So you probably are maybe familiar with Hidden-Markov-Models. If you heard Xavier's talk, then for sure. These Hidden-Markov models are these diagrams, or can be shown as diagrams, where we have these latent states that talk to each other via some transition probabilities, and each transition probability is then associated with the emission of a symbol or a token. And I've shown you here two examples with 3 and 2 states. And what this framework tells us can be shown in the plots below, where for the time being, if you're not familiar with the framework, don't pay attention to the X or Y axis, and just focus on the dark blue line, where you can see that it has a particular structure, namely it has these threshold effects. So what the line shows it's an information theoretic curve that describes the coarse graining of this process, where going from right to left, so decreasing on the x-axis, you see these threshold effects occur and the values of the line drop. That coincides with this process becoming more and more coarse-grained. And the way that that occurs, according to this framework, is in these jumps or hops that are not continuous, importantly. And the idea or the motivation was, well, can these jumps, or maybe you can call them phase transitions, be associated with the phase transitions and the jumps, if we would call them that, that we see during the training process in transformers? And if we can make that connection, then we can draw on the understanding, on the theoretical understanding of these predicted curves here to characterize phase transitions. A little spoiler, we did not manage to find this connection yet. I'll be showing just how we reached those conclusions and what could be next future steps to maybe find a framework that works, or just to assure that there's nothing else to see. So I'll start first by giving a very, very brief introduction into computational mechanics. If you're already familiar with it, you can already tune out on this slide. So computational mechanics is, for our purposes here, a framework that is good at discovering patterns in data. So very often we might have an observation, and that can take the form of a time series. So we have various symbols that are observed at different points in time, like in this string here. We would denote that in computational mechanics with, for example, a single symbol, and importantly, a backward facing arrow to symbolize the past. And that is to differentiate it from that which we usually want to predict, which is the future, and that can be a single string of what comes next, or a single symbol, or a full string of symbols of what comes next. And we usually denote that with a forward facing arrow for the future. Now, the way that computational mechanics ensures that we discover these patterns in the data is by building so-called equivalence classes, or in the language of computational mechanics, causal states. And the rule to do so is that you group together different sets of pasts. They can differ by a single symbol or more, but the important bit is that we have, for example, two pasts, x and x prime, and if we condition on these two pasts and find the same distribution over futures, so in other words, this equation here that I'm pointing at is valid, then these two pasts belong in the same equivalence class. And we denote that equivalence class by S and a superscript of plus. So we can do this then iteratively for all other pasts that would belong to the same equivalence class and build on multiple of these items. And what this effectively amounts to is that we compress the space of our explicitly written out observations to these equivalence classes. And that is a form of compression, one could say, but it is a non-lossy form of compression. We do not lose any accuracy in prediction, because these items are maximally allow one, if one has full access to them, to still do optimal prediction at the maximum achievable accuracy. Now, this stands in contrast to the second framework that we want to employ, which is rate distortion. And I'll explain in more general terms first what that is, and then in more concrete terms for the particular frameworks that we want to look at. So rate distortion. We can look at this very simple sketch here, and we start with an original information source, which I denote here by X. This can be a string or something else. Sorry. And we want to pass this through some channel, and that channel will, in general, have some finite capacity, either because of the way that the system is constructed, or just because we want to have a more efficient version of the symbol by compressing. And therefore, in this channel, we will have a new representation of our information. Now, this representation is compressed and it is lossy, and we denote that by R. And this transition, or this mapping here from our initial X to the R, can be many things. It can even be deterministic, where we have a code book that's translating between the two. But for practical reasons, combinatorics, even if there is a deterministic code book, you would always usually model these variables X and R by using random variables. Okay, so what happens is that we compress our information into R. And what that leads to is that if we, for example, would want to reconstruct the original information from which we started out from by only using the lossy representation R, then we would get this X hat, and our X hat would not be equal to the original X. So we lost some information along the way. Now, in other words, that would correspond to introducing a distortion due to this compression, to this lossy compression in this case. And there are different ways you can define distortion between different variables. For our purposes here, though, we will initially define it as a difference measure between X and R. And I leave that general here, and we'll give a more concrete definition later, because in general, you would adapt this measure to the particular problem that you are looking at. The converse measure that you would also be interested in a case like this, in addition, so to the difference measure between these two variables, would be also the actual amount of information that is retained in R from the original information source X. And this can be given then in terms of the mutual information. So this information theoretic measure, the mutual information between X and R. And usually the goal would be that if you want to have some optimal behavior of your system, you would want to minimize the amount of information that you need to remember to predict properties of X, while still keeping the expected distortion below some value D, some threshold value D. And this can be put into more concrete mathematical terms. I will not describe them in detail here, but the relevant actions are that we find a probabilistic mapping between R and X. So in other terms, a conditional probability of R given X, by minimizing an objective function that regulates the relationship between the rate and distortion. So it's given in terms of the rate, so the mutual information shown here, plus a Lagrangian multiplier times the expected distortion measure. And this object is defined separately for each value of beta. And what one would do would be that you would scan over different values of beta. Beta intuitively is a lever that allows you to place in more or less distortion into your system. At least that's how I'd like to think about it, because it's helpful for me. And you would get that for each value of beta, you would optimize you would minimize this object and find the optimal value for the rate and distortion. Okay, so now I want to change this item a little bit more by introducing a concrete definition for our difference measure that will lead us to our causal rate distortion. To do that, I introduce a new relevant variable, y. So far we had been working with our initial information source X and the lossy representation of this information source once we have compressed our information R. This new relevant variable is relevant to both of these. This new relevant variable y is relevant to both X and R. And we can think about it as some future, as the future. So the next string, if X is denoting a sequence, the next symbol in that sequence, for example. And then for the distortion measure, we can choose an information theoretic flavored measure, which is the KL divergence between two distributions. If we want to call it true distribution, where conditioning on an explicit realization of the past X, we predict the future or some future property. And we take the KL divergence with respect to the probability distribution, where instead we condition on the lossy representation R of X to predict that very same variable y that encodes some future property. The rate remains the same. With some algebra, which I don't go into the details here, one can rewrite the objective function And again, we find a probabilistic mapping between R and X that now, just for our purposes here, maximizes instead of minimizes the objective function. The rate is here again. The Lagrangian multiplier comes in with a -1 sign. And this other object here is a proxy for the KL divergence. And you can get it from taking the expectation value of this measure, placing it in terms of the mutual information by using equivalent relations, and we would find that this object is comes in with a negative sign if when we want to express DKL in terms of this object. So if this is big, then distortion is small, and vice versa. And now we have this object that is only in terms of the variables we care about. So X, our initial information source, the lossy representation R, and this relevant variable Y that encodes future properties and is relevant to both observables. Okay, so with that being said, we can then move on to the actual framework that we care about. So causal rate distortion, we have now all the tools to do so. This is based on the paper that I showed in the very beginning from Marson and Crutchfield. And as a little recap, in computational mechanics, we had these explicit histories over the past. We mapped those onto these equivalence classes, and that was a form of non-lossy compression. Now with causal rate distortion, we take these equivalence classes or these causal states, and instead of compressing the sequences themselves, we compress the equivalence classes or the causal states into some lossy representation R thereof. So I have the same measures as I did before, the rate in terms of the causal states now, and the distortion. And here again, I have shown the KL divergence as they chose in their paper between two distributions. The first distribution is again the true distribution. So we have we condition on causal states that group together pasts, and I've shown here just to, because the notation can be a bit heavy, what they correspond to predict causal states that group together futures. And we take the KL divergence with respect to, as we did before, the probability distribution, where we condition on the lossy representation of the causal states that group together pasts to predict the causal states that predict the future. We plug that into our objective function to find the probabilistic mapping between the relevant variables, and that is how we come up with these plots, which I showed in the very first slide. And now you can recognize what the X and Y axis belong to, namely beta is the Lagrangian multiplier. For higher beta, you would get lower distortion, and for lower beta, you would get a lower rate, and that can be taken away from, hopefully from this objective function here. And on the y-axis of the plots, you have the rate. And again, we focus only on the dark blue curves. Those are the curves that are calculated with causal rate distortion and the theory predictions that we make with that. And we see that, for example, for this process here, we have two transitions, and that is because we have three states, and at higher beta, we can crisply distinguish between all different states. And as we lower beta, so we introduce more distortion, we get these jumps to the lossy representations of the causal states, where by the end we have something that's similar to IID. And similar for this other process, we have one less state, so we would have one less transition. So hopefully this gives some background into the motivating work from which we wanted to start off from and compared to when we move on now to the second part of the talk, which will be the experimental results and how they compare or not, or how they're similar or not to this. Okay, so we want to adapt the rate distortion framework to the transformer setting so that we can make some meaningful analogies and calculations. And I'd like you to first focus on this little sketch here at the very bottom, where we start off with some sequence. It can be, for example, a binary sequence, as it is in most of the examples that I will show. And if we pass the sequence through a transformer that we've trained on a data set from which we sample the sequence from, the transformer would be able to tell us what the next token prediction or the next symbol in the sequence would be. We can do the same thing with the Hidden-Markov model. So our ground truth from which we generate these sequences from. And that would also spit out a prediction for what the true next token should be, at least in some statistical sense, this would be true. And in the context of the transformer, then a very simple way to define distortion or converse distortion would be via predictive accuracy, where we just take the values of these two outputs, and if they're equal, we set the accuracy to 1, and if they're not, we would set that to 0. And then the optimization problem, if we want to do theoretical predictions with this framework, would be to find the minimal rate so that we're able to communicate information above a certain accuracy threshold A, as opposed to below some distortion measure D, distortion value. So this framework, rate accuracy, we can call it, is borrowed from another work from Marson and Crutchfield, which I've shown here on the left-hand side. The formal equations I've also given here, but the important bit is that now our distortion measure is the predictive accuracy, and the rate would again be given in terms of this mutual information. And I've showcased here for the case of the even ones process, how this rate accuracy framework, predictions from this framework, would compare to the previous rate distortion framework that I discussed in the last slide for causal rate distortion. So we have the same picture that I showed in that slide here for the previous rate distortion framework. Again, just focus on the dark blue line. And we see on the left-hand side that for the rate accuracy framework, we have, again, a single transition, as we do here. In the blue curve, that is the rate curve. It is somewhat smoother, and that's for reasons that I cannot fully explain, but it's an artifact. It's just a numerical artifact of how the optimization procedure works. The same optimization procedure would work for these new definitions of distortion in this case. So we can confirm that there is some correspondence because we see that there is the transition, the single transition in the two different frameworks for the same process. And with that, we would want to move on and discuss results and look at what the transformer training dynamics actually show. And the two questions that we are interested in answering here for the validity of this theoretical framework for the experiments are, first, how does it compare? And specifically, like a quantitative measure we could look at would be to compare the number of transitions that are predicted by rate distortion, theoretically, to what we would actually observe in the training process, and whether we can find some connection between the two. And secondly, whether our chosen measures of rate and distortion provide some complementary information, specifically complementary information to more traditional measures, like, for example, the loss. Okay, so the setup that we chose to work with was a simple one layer, one head plus MLP transformer with a context window of 10. And we trained on the so-called even process, which you've seen a couple of times now and is defined by the simple hidden Markov model diagram. And the rate and distortion. Distortion is the predictive accuracy as discussed before, and the rate we calculate by taking the predictive entropy over argmax predictions of the transformer. I will not go into the detail of this unless there's any questions, but this does correspond to the mutual information between the past information source and the between the transformer predictions and the HMM predictions, sorry. So you can see the results of the different metrics on the right-hand side here. And you see them as they evolve during the training as a function of the training step. And you see the validation loss in red, the training loss in yellow, and that is in linear scale, and that's why it looks off compared to the other measures. And then there's also the validation accuracy in green. This is just our distortion measure, but also the normal accuracy that you would calculate if you would train this transformer model without having the rate distortion framework, and the rate in blue. And what we see here with a lot of these measures coinciding in a lot of places is that there are several transitions as opposed to a single transition for the single process. And also that although we see some correspondence, for example, between the rate and the transitions that occur in the loss, for example, at 10 to the 4, there are more subtle transitions that seem to be occurring later in the training that are not fully well captured by this definition of rate and that are somehow more difficult to interpret what is going on there. So we wanted to look at this a bit more in detail. We conducted a lot of different experiments. I'm going to discuss here a particular one where we asked the question on when the even process is learned, because this would provide some information on what these transitions are doing and whether they correspond to a version of the causal states that we want to know. So I have two plots here, and they're also showing some metrics, which I'll explain in a bit during training. And they're related to signature probabilities of this process here, which is defined in terms of two states, A and B. State A is associated with two different transitions, 0 and 1, and state B is importantly associated with a single transition, meaning that this process can never actually have emissions of single strings, of single numbers of ones. Pairs of ones will always come in even, or ones will always come in even configurations. And that we will use to recognize these states. And we do that by, for example, if we go up to 4 symbols, and we will have more after this, but we have the case, for example, where there are only 4, and we have a 0, then we know that we are in states A. And we can then know what the probabilities should be for emitting a token of 1. And that is what we do up here. So we recognize state A, and we condition on state A first by recognizing that the last token is a 0, and that is this dark red curve that you see here. The second way that we can recognize state A and condition on it is by observing an even string of ones. It can be 2, it can be 4, 6, or a bit more. And I've chosen to separate that because this intuitively should be a harder pattern for the network to figure out. And that is the light blue, the light red curve that you observe here. And indeed, that one approaches the true probability of 1/3, which is shown in the dashed curve. It approaches that probability later than the dark red curve. The lower plot conditions on state B, And state B has a simpler rule, or somewhat, in that you need to recognize whether the last token or the last symbol or the last sequence of symbols is an even string of ones. And here you can just focus on the dark green line because these two lines give the same information. And that is conditioning on state B. What is the probability of emitting a 1? The true probability is 1. And you can see how this approaches, how the transformer predictions approaches this true probability during training. So some observations here, and I'm showing again the other training metrics for comparison. Again, here we can recognize that multiple transitions occur, and as these transitions occur, the transformer predictions come closer and closer to the ground truth probabilities, and this occurs at different steps. We can think of this as these successive transitions achieving better approximations to the causal states up until we have full agreement, at least for this simple process. And importantly, then again, we can find that especially the later transitions are not well captured by the rate and to some extent also by the accuracy, whereas we do see some subtle changes in the validation loss. So we also looked at other processes to confirm our findings with respect to the different number of transitions and how our metrics perform. And I'm showing here the results for one process, and that is the crowd favorite in our circles, at least, MES3, with the famous fractal. The setup is the same as before. Now we're training on this different process. The ground truth in this particular configuration of the MES3 that I chose looks a bit different from, or looks different from what you would find in the residual stream from the simplex that you would find there. But aside from that, you still find the simplex. We use the same framework, and you can see the metrics shown here. So again, the rate is shown in blue. And unlike the previous case, what we find is that, at least for the loss and the accuracy beyond 100 training steps, not a lot seems to be happening, not any transitions. And there's, at least to our understanding, not a lot of interpretable things one can say about the rate occurring towards the middle of the training. But what we do find by just doing simple PCA or linear projection is that the simplex forms somewhere around here. So where this rate metric seems to be stabilizing. So this is one case where we could find that this metric does coincide with what I highly suspect to be a phase transition. One would potentially need to do something more rigorous here to verify it, like maybe run a local learning coefficient, but I would predict that one would find a phase transition that is occurring there that is not well captured by the accuracy and the loss. But here too, we see that there are multiple states. There are some states that there are multiple states in our initial model that would be our causal states, but there are at least visibly fewer transitions that do not correspond to the number of states that we would expect. Do we have some alternative formalisms in addition to rate accuracy? Because so far we've been looking at this very specific definition of rate and distortion in terms of converse distortion, which is accuracy. There are many. We chose to look at one particular other formalism to check whether that could have some additional insights. And we went for what we hope to be a more intuitive definition of the distortion measure, now a continuous one, where we take the KL divergence between the transformer prediction distribution, where we have a certain context of the given sequence, and given that context, we take the softmax and predict the distribution over next token predictions. And we can do the same thing with the hidden Markov model by just taking the context, following the transition rules of transitioning to different states. And then once we are at the end of that context, and taking the distribution over, over next tokens. For the rate, so we hope that this definition of distortion is more intuitive, specifically because it is closer to the training objective. For the rate, we chose a definition that is given in terms of the entropy of the BOS token minus the conditional entropy of the context to predict futures. And the definition of rate could be better, and we have specific ideas on how that could be better and extended. But for the purposes that we have here, which is just to make a quick check of this framework and to see whether it does provide any insights, it is sufficient. And you see that I've shown the results here. The rate is shown on the right-hand side plot in blue, and the distortion in yellow. And on the left-hand side plot, you just see the metrics that were there before. So there is no change here. The validation loss in red, which is strikingly similar to this distortion measure. And indeed, they are connected by a factor. And the accuracy is shown in green. Here too, we find that the rate definition follows and has multiple transitions as opposed to just a single one, and that at least immediately we do not see any complementary values for using these metrics as opposed to the traditional metrics. So our takeaways from this from evaluating at least these two rate distortion frameworks that we have looked at are that we have not managed to be able to find any complementary value, primarily because we cannot determine a connection between the number of predicted transitions and the number of observed transitions, even in a partial form. And we do have some alternatives here that could present some potential extensions of this work. The first alternative, which would be a direct extension, and which I would have more hope in, would be to well, it's a more subtle aspect of computational mechanics, which I haven't quite introduced when I introduced the topic. And it would be to include so-called transitory causal states in the rate distortion formalism. So what they are is that, so starting from the generative process that we've been looking at so far, this is what we use to generate our data by letting it evolve and getting the different emissions of different symbols. But out of this process from first principles, you can derive a predictive structure, which is shown here for this simple process on the right-hand side. It can be a lot more complicated for more complicated processes, but for the simple process, it takes this form. And you can recognize the generative process here. These are our causal states, A and B, in purple. But there are additional states, and these are so-called transitory causal states, and they are necessary because in this optimal prediction structure, they are used to resolve ambiguities. And the ambiguity in this process would be if we had, if the first symbol we observe is a 1, and we keep observing 1s, this would be this loop here, we don't really know whether we're in state A or B. And once that ambiguity is resolved, which will eventually happen by observing more symbols, then we can recognize which state we are in, and we would find our causal states, our infinite time causal states. But if we would include these transitory causal states in our formalism, we would expect to have more transitions, and therefore maybe also be able to find a better correspondence between the observed transitions and the theory predictions from this extended formalism. The second alternative is to choose yet another different rate distortion framework and not only change the definitions of rate and distortion measures, but also change the optimization algorithm, which I haven't gone into a lot of detail here. And if one would have stronger intuitions on what the training process should what the training process is doing and translate that into concrete quantifiable rules for the optimization, then maybe the theory predictions from a different rate distortion framework would be providing better correspondence with what we see in experiment. But that I personally find to be hard, but I think it's worth mentioning. For future work, and this is one of my last slides, I want to discuss a little bit what would be the next steps that we would take. We would probably, not focus anymore on rate distortion unless we find something new that is hinting at something very promising. But for now, we would focus on actually trying to explain just what these transitions are corresponding to and do more experiments in terms of trying to connect these transitions to causal states or to the causal states or the transitory causal states by using different methods. We also can find that if we break down these metrics in terms of context position, there are 10 context positions in our case, and I'm showing here all of them from 0 going up to position 9. And you can see how the metrics of loss and accuracy look for these different context positions, and specifically that the number of transitions seems to increase. This is an interesting finding. We have various different methods that we're excited to try out here. There is also work that has found similar looking transitions in deep linear networks. There's a really nice paper from Sachs et al. That connects these sort of transitions where you have plateaus and then rapid transitions in the accuracy metric to singular value learning of the matrix that's being learned in their deep linear network. So something flavored along those lines or different, we want to look at a bit more in next steps, and we think that is more promising than focusing on rate distortion for the time being. So with that said, that brings me to my final slide of summary and open questions, which I've discussed to a large extent recently. So from causal rate distortion for characterizing phase transitions, at least for the two frameworks that we found or that we used and adapted to transformers, we found no substantial complementary value to recognizing relevant phase transitions compared to conventional metrics. And of course, to be able to be more certain of this, we could run a metric like the local learning coefficient and compare to that. We find no clear correspondence also between the coarse graining of causal states via causal rate distortion and the observed phase transitions during training. And I've suggested some alternatives just before, and those can be meaningful ways which one could look at if one is interested in pursuing this line of research. But for now, we will focus on other means to explain these transitions that we're excited about. So yeah, that concludes my talk. Thank you very much for listening, and I'm open to questions. Yeah, Carlo, please go ahead.
Can you explain intuitively what these, like how to interpret these transitional states?
You mean the transitional states as in what is occurring in the coarse graining of rate distortion, or?
No, in the previous slide where you
Yeah. Here.
maybe previous as well.
Previous.
Yeah. Yeah, the
These things.
transitory states, yeah.
Yeah, so these states are so these states are necessary if so an optimal predictor that wants to that has only as information the consecutive strings. So like you have 0, 1, 1, 0, 1, 1, 1, something like that. That's all you see. And you see them one after the other. And you want to do optimal prediction on this string to be able to find which of these states you find yourself in. And if you want to do that, you cannot immediately start your prediction in these states, since that is what you want to find. What these transitory states allow is this additional computational structure to be able to resolve ambiguities that are inherent in the generative process. So if you would start, if the first thing, so you start here, this is your stationary distribution, and if the first thing you observe is a 0, then you recognize that you are in state A, as labeled here, and you do not come back to these transitory states. Therefore, the name transitory. And you would just do your belief state updating according to the generative data structure in this very simple case. But if the first symbol that you observe is a 1, then you could be in state A, because state A can emit ones. State B can transition to state A with a 1, but you could also be in state B, because state A can transition to state B with a 1. And since you don't know that, you need to keep track of this ambiguity separately until you have resolved it. So you observe a 1, you have not resolved the ambiguity, so you have these additional transitory states to make up for that. You observe another 1, and you're still in this ambiguity mode, and you keep going until you observe a 0, either here or here. Is that making more sense, or is that just saying the same thing?
Yeah, so they're like epistemic
Yeah.
states. Okay, yeah.
Yeah, that's quantifying your epistemic uncertainties and trying to resolve the ambiguities. Yeah, that's correct. Xavier, yes, please.
Hey, Yasmina, thanks for the nice talk. I'm wondering if you can comment on the connections between this work and possible applications of singular learning theory to this context. Like, is the local learning coefficient something that you may consider complementary to this framework, or completely distinct, or something else
Yeah.
entirely?
Ideally, whatever findings we would get would be complementary to the local learning coefficient. I have not run it because I've at least you can never be certain, but I've thought that the information we get from these metrics, like the loss and the accuracy, are to a large extent sufficient to recognize phase transitions. And I've also seen that with other metrics, like these probabilities that I was discussing about before. But clearly they don't always capture all the transitions that occur, and the local learning coefficient would be telling you where these transitions occur and giving you some other sort of information, like the model is more complex or less complex depending on how the shape of the local learning coefficient curve is. The ideal version of the findings of this project, though, would have been complementary to that and would have wanted to characterize phase transitions in a more quantitative way than just being able to herald, like, oh, this is where the transition occurs, but also being able to say something more, like, the transition occurs here, and this is what the model is doing in this place, namely learning a coarse-grained or more finer-grained version. Sorry, yeah, not coarse-grained, learning a more finer-grained version of the model, for example. So that would have been, that is not the case, at least we haven't confirmed or found that, but that would have been the hope. If this was a project that would just deliver some metric that does the same thing as local learning coefficient, that would probably not have had a lot of value. So if it was phrased like that, that was probably my mistake in the presentation, and it should have been clarified. So thanks for pointing that out.
No, that's quite helpful. Thanks, Jasmina.
Yeah.